This video is going to show how if we have a region R on a graph and we want to revolve that region about an axis or a line, we can use an integral to find the volume of the shape. And this problem says that the region that we're going to be talking about is bounded by f of x equals 4x squared minus x cubed and the x-axis. And the first thing I want to do, if I haven't been given some kind of visual to use, is to sketch a visual for myself. And in this problem, it's helpful for us to factor f of x. We get f of x is equal to x squared times 4 minus x. And then we know that our region, let's let it go out to 4 on the x-axis, and I'll leave the y-axis unlabeled. I know that I'm going to have a region R that looks something like that. The double zero at 0, because I have x squared here, is telling me that I'm turning around at the x-axis at this point, so that's how I know the general shape of the curve. And the problem tells me that I'm revolving the curve around the x-axis, so I can sketch on kind of a mirrored shape here, and then know that I'm going to be taking intervals of the region R and spinning them around the x-axis to make disks. And each disk is going to have a surface area on the top and bottom. That's the same. And formula for area with respect to x is going to be the area formula for a circle, only our radius here is going to be f of x. So I have a of x is equal to pi times f of x squared. And I know that the integral formula says that if I take the integral from a to b of the area of each disk, and because we have the integral, we know that the width of each disk that we're adding up is approaching 0. And I'm going to use this formula anytime I'm making a volume by slicing. The cross-sectional area as a function of x is what I'm going to integrate from a to b with respect to x. And I've found an a of x formula in this case already, so the last thing I need to do is define my interval before I can integrate. So obviously our region starts here at x equals 0 and goes until x equals 4. That was part of what I figured out when I was looking at the factored form of the function. And so that means for this particular volume, I'm going to take the integral from 0 to 4 of pi times the function 4x squared minus x cubed squared dx. And I can pull the constant factor, the constant coefficient pi out of the integral, and also perform the operation of squaring what I have in parentheses. And that's going to give me pi times the integral from 0 to 4 of 16x to the 4th minus 8x to the 5th plus x to the 6th dx. And I can evaluate each part of that integral by the power rule for integration, right, working on each term. So I get this is equal to pi times, and I'm going to increase the exponent by 1 and divide by the new exponent. So I have 16x to the 5th over 5 minus 8x to the 6th over 6 plus x to the 7th over 7, and I'm evaluating from 0 to 4. Obviously, these are pretty huge values, so I've used a calculator to find out 16x to the 5th is 16,384 over 5. Then we have 32,768 over 6 and 16,384 over 7. And we're subtracting from these values, the values that we would get when plugging in 0, but since all of those are 0, we won't need to write them here, and we'll continue to evaluate this problem by giving common denominators and making it so that we can simplify these fractions. On second thought, this is not a problem that makes much sense to continue with working through by hand without the use of a calculator in general. So let's just plug this into the calculator and skip to the result that we would get multiplying by pi, and we have 490.208 if we round to 3 decimal places. And obviously this is units cubed, some kind of units, but units are rarely given in these problems, and they're not really expected to be included in these answers, although we know that we're working with a volume in this case. Fortunately, when we are asked to do something like this, so the expectation for this problem with this kind of computations is that we're going to be using an definite integral function on a graphing calculator or in some kind of computer system. So we're able to go from this step where we've written our integral and just go straight into the calculating functions for definite integrals in our graphing calculator and end up here at the same result that we got, kind of showing how to work through part of this by hand, reminding ourselves of some steps for integration. So there's a volume of revolution revolving around the x-axis, and hopefully in a future problem we'll look at what the differences are when we're revolving around a different line, something like maybe y equals -2, or maybe even revolving around the y-axis instead of the x-axis.